Alberto Martinez.
Alberto Martinez.
How long have you been?
I've been here for almost 11 years.
11 years, Alberto, in this park.
Yes.
Now, what is that you do here?
I'm the lead ranger here, which means I get to do all the fun stuff. I do everything that needs to get done here. As far as maintenance, administrative, training, safety training, everything.
Very good. And then you have volunteers.
And then we have volunteers. That is where the fun part comes in, because volunteers, when they come here, it's because they want to be here. So they're very gracious to help us. They're happy to be here. They help us in any way they can.
And you always have availability for volunteers.
We're always striving to get more volunteers to help.
Very
And there's a volunteer behind you right now.
sí.
She just went around the bookcase.
Mira.
There she is.
And your name is?
Margarita.
Margarita.
Yes.
How long have you been a volunteer, Margarita?
Since November.
Since November. And have you enjoyed being a volunteer, Margarita?
Yes, very much.
So can we go and visit schools and tell them that there's an opportunity to be a volunteer at the state park?
And we also are active in going to career fairs too, to encourage people to both apply for positions and to come out and volunteer.
Instead of being a couch potato, who said I used to be a couch potato?
Me.
You. And one day you said, no more couch potato. What do you do here?
Checking people?
Oh, so people needs to come, and very important. So visitors, when visitors come to the park, what do send a message to the visitor when they arrive? They drive through Carmen Avenue.
So when visitors come to our park, the first thing we need them to do is either utilize our self-pay station outside the gate or come into the visitor center and check in, where they'll be able to get their park pass and a map, and we'll orient them to our facilities in our park, so they'll have opportunities to enjoy us here at the Resaca.
Well, thank you so much.
Thank you.
For this super awesome energy that you all have, and for letting us be part of the park today. We're gonna keep on searching for the other team members.
They're probably in the dome.
In the dome?
Yeah.
So the dome is not gonna be, there was one day that the dome was here. So
That's
now-
the planetarium,
Caramba.
and we'll have that in here, but the actual observatory is
This
outside.
is the dome. Sorry, I got confused. The planetarium is the one you inflate.
Yes.
Yes, sir.
And they're also setting up the dome.
Yes.
Okay, very good. So let us go and visit the dome.
So right behind me, it's the dome, right? The observatory itself. The telescope that's inside is a 16-inch Cassegrain telescope. It's the size refers to the diameter of the mirror that's inside. The goals, right, that we have for this observatory itself is to make it completely autonomous, to remove the person observer. Right? But of course, we're long ways away from that. Currently, right now, it requires human operators, in which case we do everything from making the plans for the night, as well as aligning the telescope. So we'll have to be there, and we point the telescope somewhere, then we have to go over and move the dial to make sure that the dome rotates, right, to align with that. So in the future, we'll have automated processes that will deliver that.
The University of Texas Rio Grande Valley, and especially Center for Gravitational Wave Astrophysics, is one of the best places in the world from gravitational wave physics. I'm doing research on electromagnetic counterparts to gravitational wave events. So for example, if we have two neutron stars that collide, apart from gravitational waves which we could detect thanks to the LIGO detectors and Virgo detector, we can also see some flash on the sky, something that will appear and will change brightness over the time, because there is so many rich neutron matter ejected from the collision of two neutron stars that they will start forming very heavy elements that will decay. For example, this is the collision of two neutron stars is only known theoretical process to produce gold in the universe. And many of the heaviest elements that we have in the periodic table, the heaviest part, the bottom part, came from the neutron star collision. All the gold that is on Earth was a result from collision of two neutron stars some many million or billions years ago. So, the key stuff is to if we have the gravitational wave detection of, for example, we suspect that there was there was a collision of two neutron stars. The key is how to find this object on the sky, how to find this something that flashed on the sky and start decaying.
Let's imagine you have a wave that's coming at you. The effect is to squeeze space along one axis and stretch it on the other, and then squeeze and pull in this direction. But space is incredibly stiff, and the result is that this event, some 130 million light years away, only made the smallest change you could imagine. If you had, for instance, a yardstick and the gravitational wave were to pass next to it, it would change length by less than a billionth of a trillionth of an inch. On the other hand, if you say, what's the change in distance to Alpha Centauri, some 4 light years away? It changed by the thickness of a human hair. So that's how small the effect is, and that's our measurement challenge. So one of the things, though, I just said is that you get a bigger effect if you go further away. The gravitational wave is a strain in space. It's like stretching a rubber band. When you make a longer baseline measurement, you have a signal which is larger. And that's why LIGO and Virgo have arms which are miles long to boost up the signal to the point where it can actually be measured. But you still need some of the most sensitive devices that have ever been made to have a sensitivity that suffices to get a measurable signal. You also need, critically, hundreds and hundreds of people who can design and build and install and run these instruments, and then thousands of people around the world in the LIGO and Virgo collaborations who then can analyze the data and get something useful out of it. So now we're going to look at a simulation of an interferometer. We use interferometry. We compare the peaks and troughs in light waves that travel down the two arms and then back together again. Now, between the peaks of the light we use is about a billionth of an inch. But in fact, we can split that down by another factor of a billion by using very powerful lasers. Really, it's the quantum effects of light that limit how well we can do. And with that, we can actually get to a signal that is measurable when the gravitational wave passes and shifts those wavefronts by a tiny amount.
Students that I teach say that they looked up the sky when they were young, when they were little, and they enjoyed the stars and the moon and planets. And then now in my astronomy class, their interest was rekindled, and they are learning astronomy with a great interest, great fun.
I grew up with watching documentaries about science, and I noticed on the titles, it'll always say PhD, physics, right? Or physicist or science researcher in that case. And that's the thing that really intrigued me, just the mysteries of the universe. And my parents dropped me off over at the university, and it must have been my freshman or sophomore year. They were doing modeling of black holes, what happens when black holes merge. And I guess the numerical models hadn't been done and computed. And UTB, I just so happened to find them in a magazine as I was flipping one summer through the magazine. It must have been, one of the major national magazines, and it said there, photo courtesy of UTB. And I was thinking, I'm here. This is amazing research that's happening right here at home. And that was something that was pretty amazing. So then I had an awesome opportunity through the Math and Science Academy to finish my junior and sophomore year of high school at the university. And right there, I entered and declared major as physics. I currently hold a Bachelor's of Science in Physics. I am just a thesis away from having my master's. And I am enrolled in the cooperative program that UTRGV had with UT Arlington. So I can do my studies here, but I'll get credit and I'll have my doctoral degree offered from UT Arlington.
When we get the data in the different optical bands, we need to analyze it to better understand what was behind it. For example, if we have the one of the biggest discoveries of the last year was discovery of the gravitational wave, which was 170817, which was the collision of two neutron stars. This was the first ever recorded event, both in the gravitational waves and in the optical band. And why is this is so interesting? Because gravitational waves give you the information about the motion of the mass in the source. It has to be very dense, has to be very heavy. So it should be two neutron stars or two black holes, or neutron star or black hole. And information how those objects collide are in the gravitational waves. But if you're asking what happened afterwards, what happened afterwards, the optics give us the answer. In the optics, for example, if the neutron-rich matter is ejected, we can see how it changes, how the spectra changes, and this gives us information about how the process of forming the heaviest element is going on. And if in a few, maybe not if, when in the few upcoming years we will observe gravitational wave signal from the supernova inside of the LIGO and Virgo detectors, we can in fact look inside into the star that is collapsing. What was the engine that drive the core collapse into the explosion? How it was going on? This would be the question that we would like to answer in the upcoming years. But up till now, what we are doing is this is something very new. The first detection of the merger of two neutron stars was last year in the summer, in August. And the team from the Center of Gravitational Wave Astronomy was giving also have a contribution to observation of this event. We took the images, we analyzed them, we published the paper along many other teams in the world, like Harvard University, the Caltech, and the others. Our research were also big contribution to the discovery. But this is the astronomical part. This is the part that the work of the Torres team, which is the optical project of the center, works in, and this observatory is also the part of the network of the Torres telescopes. We are building now the other observatory, which would be in Argentina, in Andes, and we hope to get this operational in the fall. Maybe so not very far from now, but still there is about 4 or 5 scopes that also work with us. We are working with the Torres is an international project, but led by the Center of Gravitational Wave Astronomy, and we already make a contribution to the many stuff connected with the gravitational waves. The center is also doing a lot of stuff in the detector characterization of the LIGO detectors and so on. So there is a many fronts that the center is working on. What I am doing is connected to the observation, how to efficiently observe the electromagnetic counterparts, so flashes in the sky that is connected to the gravitational wave events, and how to extract as much knowledge as we can. What we are planning to do for the next LIGO observational campaign is to have artificial intelligence that would help us to make the data analysis faster. It takes months or in a weeks if everybody is working on that and put aside everything. It's not only our team. It's also the same with the other big universities. It takes time.
We are planning to make several number of telescopes that can be controlled remotely. So telescopes will be there, but we will control the telescopes from anywhere in the valley or even from any place all over the world, as long as there is an internet connection. We move the telescope using the electronic device. We take the picture, we analyze the picture and do the astronomy research.
Having that opportunity to engage with Texans and help them to enjoy this resource and to look through a telescope, maybe for the first time ever, and to learn about our cosmos. We're all part of a much bigger world, and it's easier to see it with a big telescope.
If you don't get excited about this and you watch what you're doing, like tonight, look at that. Look at those kids. they're here. They're not watching a PlayStation. They're outdoors. They're going like, what is this all about? You know, and that's good. That curiosity. This is a beautiful place to have it. It's a perfect place to have it. And so I'm excited because what happens is not only will you be able to see nature on this earth and this planet, but you'll be able to see beyond the stars. You know, I mean that to me is awesome.
The big advantage of this place is obviously the dark sky, where there is no bright lights from the houses or from the street lights or from the vehicles. So it's a perfect place.
The UTRGV and the center is really great place to do science, and we are very thankful for Texas Parks and Wildlife to allow us to build the observatory here and use this for future scientific projects, and also to use this facility for the outreach activities and educational purposes for the community.
We're naming it after one of my mentors who unfortunately passed away just a few years ago. Her name is Dr. Cristina Torres. And so she was not only a mentor, but also a friend. And so it's very meaningful, you know, that we're naming it after her. She was a huge advocate in outreach, you know, for everybody to have science, right? To be knowledgeable of what's around them and that they could also do it. And so that's something that's very meaningful to me. She's also been heavily active with the observatory right from the start.